Lesson 34, short circuits. We will learn about current's tendency to take the path of least resistance. Now, the path of least resistance is actually, it's almost like we refer to it in electronics, but it's also realistically, it's more of almost a philosophy of life, is always to take the path of least resistance, take the easiest path. Should you go down the path? Why should you go down the path that has a lot of resistance? Some people say, oh, the path of most resistance is the most enjoyable, or something like that. We're not going to talk philosophy today. We're going to talk about physics. So yeah, if you want to talk about philosophy, you can talk about that else another time. Last lesson we did was we powered through this new idea of comparing series and parallel circuits. We said the main thing is that with a parallel circuit, you will get, if both of these circuits are 12 volts, then each of these bulbs will drop 12 volts. But each of these bulbs will drop 6 volts. And so therefore, the one on the right, these bulbs will be brighter. And the reason that they are brighter is because they share the voltage, but they don't share the current. In fact, because and I actually showed you briefly, because it's a lower resistance, the current actually is higher, which also means there's more power is getting dropped over them. Now, I did look this up online before I did the lesson. If you create a circuit with a power limiter, a current limiter, so therefore the voltage is supplying the same voltage as the same current, you don't see this effect occur. But for this situation, you would see, we usually just say with more voltage drop, we have a brighter light bulb. We see here, this is the evidence of it showing up. And then that was it. So today what I wanted to talk to you guys about was short circuits. What is a short circuit? What does it mean by taking the path of least resistance? To do that, I always go for the analogy. Now I could show you many different analogies for this, but the path of least resistance is best done with the mountain analogy. I'm going to show you that today. Starting off, we're going to draw a mountain. So now I'm going to make sure that the mountain actually looks like a mountain. So last time I drew this for my students, specifically my year 10 students, because they do engineering maths, I showed them this analogy, and they said, sir, this just looks like poop, because I did it in brown. So I'm doing it in black. I'm going to do a thing like that so that it looks like that's the ice cap. But yeah, you probably can still say that. Now, I'm also going to do, on this picture, I'm going to do 2 paths. One path that goes up the mountain. We'll go like that, And then one path that goes around the mountain. And let's just say we've got, and the usual example I do for this kind of question is, let's just say we've got a bunch of students. Now, these could be these students want to get to the other side of the mountain, because on the other side there is a we'll draw a little ice cream shop, and the ice cream shop sells ice cream. We'll just make it vanilla because they can't be bothered drawing it. And so so these students really want to get to this ice cream shop, and the students can choose to and we call the ice cream, that's the stimulus, that's what's drawing it to the people. So that's the EMF. It's the electromotive force, it's the battery, it's the voltage of this scenario. These students really want to get to this they really want to get to this side of the fence. They really want to get to this side of the mountain so they can get to the ice cream. That's the voltage. Now we've got 2 forms of what we would call resistance. We've got the mountain, which forms one form of resistance, and then we've got the road, which is another form of resistance. Now The idea is pretty simple. Which way are students going to go? Okay, just quickly, I'm going to ask you guys this in chat, and I'm also going to unmute you. So can someone tell me, which way do you think the majority of students are going to go? Do you think students are going to go over the mountain or via the path?
Via the path.
Over the mountain.
By the path.
Via the path.
I got 3 via the paths and 1 over the mountain. So I'm going to mute you guys now, because someone's having a conversation, and we're going to talk about that. Yes, the answer is via the path. The majority of students are lazy. If I can get to this ice cream, and I would be doing this too, if I can get to the ice cream shop without having to break a sweat, and believe me, that's the path I'm going to go down. So we have a lot of students going this way. This is a high current. We've got a lot of students moving via the path of least resistance. Whereas the path of most resistance, you will get like your TANs of the world that decide, you know what, I would rather take the mountain path because let's see where it goes. And they will take instead the mountain path, and you know, they will go to see, you know, how do I get to the ice cream shop? But there's going to be far less. There is a low resistance, there is a low current of people going over the mountain. There is a low flow, few people. So what that says to me is, in this situation, the people are going to take the path of least resistance. And the least resistance, why it means the path of least resistance, is because there is less resistance on this path. Easier to go down. Now, electrons do this as well. Electrons will tend to go down the path of least resistance. I actually have a nice picture here. So we'll go back to the previous picture in a second. So if I have a circuit, right, and the circuit can go, the electrons can say, well, I can go down this path here, which has, you know, some resistance. Or I could go down this path, which has no resistance. Well, which way is it going to go? It's going to go down this path here. Most of the current is going to go down that path there. So if you can imagine it instead as a hydraulic thing, if I've got a small little pipe, the water is going to struggle to get through. Actually, 2 small little pipes, the water is going to struggle to get through. Or I've got this big open pipe at the end, the water can just flush down really easily. Trust me, most of the water is going to go flushing down this path here because it just provides an easier path. You guys might have encountered this if you're ever trying to, I don't know, do something with cooking and you're like, I want all of the water to go into this, I want all of the sauce to go into this specific little jug. And so you've got this jug and then it's just, you know, you're just pouring it in, but it just spills everywhere. It's because like the path of least resistance is not into that tiny little spout, it's everywhere else. So it will always take the path of least resistance. So what happens when electricity takes the path of least resistance? What does this create? Create something called a short circuit. So more current will pass through the path of least resistance. So with nowhere to drop the voltage, right? This is where we get a problem. Let's draw a short circuit. So we've got our battery, we've got our circuit, and we're going to do this. Right now, the most easy, like more, I could draw that wire here, I could draw that wire here, it doesn't matter. But what happens is that as the current travels, and I'm using the word current, not electrons, as the current travels, it's got 2 choices. It can go down or across, but across has no resistor, so it's going to have a lot of its current is going to go down this way because it takes the path of least resistance. So now here's the problem though. We know from Kirchhoff's law that it must drop if this is a 12 volt power supply, 12 volt battery, it has to drop 12 volts here, but this is a circuit, it is a loop. So it must drop 12 volts somewhere over this loop. And where will it drop it? It'll drop it into the wires. Now, I've told you before, the wires are very, very little resistance. So therefore, they don't act as places for voltage drop. But if there's nothing in the circuit, there's no resistors, there's no diodes, there's no lamps, there's no switches, if there's nothing in the circuit, then it will just drop it into the wire. Now, wires are not necessarily do the greatest job of, holding current, holding resistance. So they're going to get very hot very quick because resistance leads to heat. So if you're dropping a lot of resistance over a small thin wire, then you're going to instead heat that up and get that really hot to the point where it can sometimes burn. Now, sometimes this actually doesn't happen in the wire. Sometimes this actually happens in the battery. You can actually get a short circuit which can lead to high resistance through the battery. Because believe it or not, the battery also has a resistance. And if you get a high resistance in the battery, then you can actually get the battery to explode, the battery to heat up. And that's also a bad problem. If you ever just take a battery, did someone say something? I don't think so. If you just get a battery and you hook a paper clip up to it, you will find two things. One, that paper clip gets really, really hot because you've short circuited the battery. But you will find afterwards that that battery gets really hot as well because the battery also is going to drop some of the voltage through it as well. So you end up with both of those things getting really hot. So that's what a short circuit is. A short circuit is just a path for it's a path of virtually no resistance, a path where the current can go down without anything bothering it. I want to show you this quick video because if I can, it depends. Give me a sec. Now, I normally show this to students, but I'm going to skip to one in particular. This one here does the best job of sort of showing off what a short circuit is. Here we've got two wires, yeah? On these wires, these are electrical wires. So one of these wires is meant to be positively charged. One of these wires is negatively charged. Now, that's normally fine, it doesn't matter. And that's why I said, I think I remember talking about an example is if a bird's sitting on here, it doesn't matter that the bird's sitting on there because it's got a zero potential difference. But this stick is another business altogether. It's instead branching the two wires. So it's now become a short circuit because the electricity could instead go through these wires, or they could instead go through a house. And it's like, okay, well, which one's got less resistance? I think the stick's got less resistance than going through a house. So if we watch what happens, you should be able to see if I unclick this. It's getting really, really hot. That hissing sound, that's water escaping. And that is an electrical arc. That electrical arc is, of course, once the stick is burnt, it then has to conduct the electricity through the air, and it's going to make a plasma, and that's going to conduct electricity that way. One more example. I like 2 as well. 2 does a pretty good job of explaining something. Same idea, except, wait for it. That was a stick hitting the wire, and then that arc just goes on for a while, and a lot longer than you would normally think an arc would probably go for. But yeah, that's what the power of a short circuit is. Short circuits are just a way that you can, it's a way that the current can go through a circuit without actually going through the individual resistors. Now, ladies and gents, that was the only extra part that I wanted to talk to you guys about.